Peridot Mesa is one of Arizona's most famous gem-producing areas. Access to the mesa must be acquired through the San Carlos Indian Reservation office in San Carlos. However, access does not allow anyone to collect. Through the efforts of Stevie Joey, a Navajo Apache tribe member, visitors to the mesa, under his guidance, are allowed to collect on his claim for a fee. It was through Stevie Joey's permission that samples were collected and photos were taken for this presentation. Peridot Mesa is located about 100 miles east of Phoenix, note the green star, and lies entirely on the San Carlos Indian Reservation. Peridot Mesa is the result of a volcanic eruption that took place between 2.5 and 5 million years ago. This Earth Explorer satellite view shows the position of the volcanic vent at Peridot Hill and the lava flow that extended north and east from the vent. Stevie Joey's claim position is also shown on the mesa. This is a shaded topographic map view and nicely shows the extent of the lava flow. The blue line is a dirt road that leads north from State Route 70 towards the claims on the mesa. From this topographic map, a profile of the volcanic vent and lava flow can be made. Here the red line represents the position of the profile line. This image shows the relief depicted by the contour lines on the map. And finally, it is rotated down to the bottom of the slide for a more conventional view of the profile. From field observations, the different kinds of rocks can be mapped on the mesa to produce a simple geologic map. Peridot Mesa itself consists of a type of basalt. Here it is shown in green. Beneath the basalt of the mesa is a layer of conglomerate that is shown as brown. The conglomerate lies below all areas of the lava flow. In fact, the lava flow is a protective, hard cap rock that prevents the underlying rocks from weathering away. In this case, the sedimentary conglomerate represents the material of an ancient lake in the area that existed prior to the eruption. As you can see, the sedimentary conglomerate is visible all around the extremities of the lava flow. This red area represents the volcanic vent rocks. It consists of fragments of rocks that were created during the violent explosion, as well as pieces of foreign rocks brought up from great depths below the crust. It also contains large amounts of cinders created during the eruption. This view shows the volcanic vent called Peridot Hill. With an elevation of 3,231 feet, it stands about 300 feet above the surrounding terrain. This view is from the dirt road just north of the highway and looking to the north. Geochemical evidence suggests an eruption date during the Pliocene epoch, some 2.5 to 5 million years ago. An analysis of the erupted rocks that make up the vent and lava flow indicate that the eruption was very explosive. This diagram shows the initial phase of the eruption with the lake shown as a blue layer. Most likely the magma that created the eruption was highly charged with gases. Probably carbon dioxide and water as superheated steam were the most abundant. As the molten mass migrated towards the surface, it created fractures in the rock above it. It was along one of these fractures that the gas-charged liquid rock forced its way to the surface. In doing so, the trapped gases rapidly expanded, created an explosion that fragmented the wall rocks of its vent and spewed solid material along with excessive amounts of gases into the air as a huge glowing cloud of volcanic debris. This slide shows the continuation of the eruption with a buildup of fragments that would become Peridot Hill. Clouds of rock fragments and molten bombs continue to be jettisoned during this phase of the gas-rich eruption. As the eruption continued, the gas content of the liquid rock began to decrease. This allowed a lava fountain to form. This fountain of molten rock was directed towards the north and east and is responsible for the formation of the mesa. Note also the lava flow shown in red on the right side of the diagram. This is called a rootless flow in that it is not directly connected to the vent. Instead, the fountaining created enough hot material that, as it accumulated, was able to flow down the natural slope of the terrain. It is in this flow that the peridot-bearing nodules are mined. After the eruption ceased and the rocks began to cool, portions of the sides of the volcano fractured and slumped into the vent. A circular fault has allowed the inner part of the vent to drop some 50 feet in places. This is the view we have of the volcano and its lava flow today. This is a view from near and north of the vent looking north across the edge of the lava flow. The vehicle in the background is on Stevie Joey's claim. The view is typical of the edge of the flow. The lower slope of the hill, especially the one in the foreground, shows some of the brownish lake bed sediments exposed through the accumulated pieces of basalt that have been eroded from the flow above. Again, from the north of the vent, This view shows a better distinction between the lava flow associated with the vent and the sedimentary lake beds below. This view is looking towards the south. As the volcano erupted, it carried upwards, from great depths, fragments of peridotite. Peridotite is an igneous rock term used to describe a rock that is coarse-grained and rich in olivine. However, the term is a family name and includes different varieties. This is a fundamental diagram that shows how ultramafic rocks like peridotite are classified. Note that the top of the diagram denotes rocks that are 100% olivine and 0% pyroxene. As you glance down to the bottom of the diagram, the percentages reverse and pyroxene becomes 100% and olivine is 0%. If the igneous rock in question has anywhere from 40 to 100% olivine, it can be classified as a peridotite. The remainder of the peridotite typically contains pyroxenes, calcium-rich feldspars, spinel, magnetite, diopside, and other minerals in minor amounts. If the rock has less olivine, 0 to 40%, and is 60 to 100% pyroxene, it is classified as a pyroxenite. As the name implies, it is dominated by pyroxenes and can be distinguished from peridotites by its darker color. Peridotite and pyroxenite are the main divisions, but they can be further divided. For example, if the rock is nearly pure olivine, 90% or higher, it is classified as a dunite. Its location on the diagram is at the top. If the rock has less than 90% olivine but more than 40%, it is classified as a lherzolite. The vast majority of peridotite nodules at Peridot Mesa are actually lherzolites. With less than 40% olivine and increasing amounts of pyroxenes, the rock is classified as an olivine websterite. Finally, with 10% or less olivine and at least 90% pyroxenes, the rock is considered to be a websterite. Websterite is named after the town of Webster in North Carolina, where this type of rock was first scientifically studied. So, armed with a basic knowledge of ultramafic rock classification, the previous rock can be seen to contain at least three different coarse-grained nodules. They are peridotite variety lherzolite, peridotite variety dunite, pyroxenite variety olivine websterite. This is because this particular nodule has greater than 10% olivine. And the matrix rock is a basalt of the variety basanite. Basanite is a type of salt that is very poor in silica. Although the percentage of silica in this chemically analyzed basanite is 46%, it is considered to be very low in silica. The percentage of oxides is shown in decreasing amounts. The first emphasis of this picture is the basalt. The abundant holes are called vesicles and are created by bubbles of gas within the lava that were frozen in place as the lava cooled and crystallized. The great number of vesicles lend their name to this variety of basalt, vesicular basalt. Their abundance implies the explosive nature of the eruption. The higher the gas content of the liquid rock, the more violent the volcanic eruption is likely to be. The gases in modern volcanic eruptions are dominated by water in the form of steam and carbon dioxide. It is assumed that these were consistent with the gases associated with the eruption from Peridot Hill only a few million years ago. The second emphasis is peridotite nodules. These are rocks that were brought up from great depths below the Earth's surface and included as solid inclusions within the lava flow. They did not form from cooling of the lava. Geologically, these are called xenoliths. As molten rock moves within the Earth, it can rip off portions of the surrounding rock walls. If these rock fragments remain intact and are not entirely assimilated into the liquid rock, they are called xenoliths. The term xenolith is from the ancient Greek xeno for foreign and lith for rock. Any rock or mineral fragment derived from the walls of the rock chamber and then frozen in the igneous rock is a xenolith. The question then becomes, where does the silica-poor, peridotite-rich lava come from? The answer is deep below the crust of the Earth. The olivine grains that dominate the peridotite form deep beneath the crust in an area of the Earth's interior called the upper mantle. In this diagram, the Earth is divided into layers based on composition, density, and physical state, that is, solid or liquid. The upper mantle is theorized to be the source of the xenoliths. In this enlarged view of the upper mantle that extends to a depth of 415 miles, it is separated into different zones. Below the crust is a zone of higher temperatures and pressures where serpentine dominates. With increasing temperatures and pressures downward toward the Earth's core, the serpentine gives way to more stable olivine and then to spinel. The current theory for the origin of the xenoliths in Peridot Mesa is that the volcanic eruption was deep-seated, meaning that the molten rock was derived from perhaps 60 or more miles below the surface, from the top zone of the olivine layer. This is geologically very significant in that we are not able to directly sample levels below the crust. Thus, the volcanic eruption at Peridot Hills provided valuable geological samples that help refine theories of how high temperatures and pressures dictate mineral structure and formation. Each xenolith then represents a fragment of the wall of the volcanic conduit deep below the surface from which these scientific treasures traveled. Typically, the nodules are dominated by olivine. Spinel, orthopyroxene, and chromium diopside are also commonly found. This slide shows a nice olivine fragment and its physical properties that are useful for its identification. Gem olivine is called peridot. Another common mineral found as xenoliths in the basanite and within the peridotite nodules is spinel. In this rock, two large spinel xenoliths are clearly visible. The spinel fragments are black and nicely display conchoidal fracture. This view is of a remote, pristine area of the mesa. It shows through natural weathering processes residual pieces of basanite, olivine, and spinel that were released by the disintegration of the basalt. Quarrying in the area constantly exposes fresh material. The mining is done solely by tribal members who have claims on the mesa. The majority of the mining process is done by hand. Here are some of the tools used by Stevie Joey. This is a close-up view of a peridotite nodule showing the gemmy olivine grains along with a few chrome diopside grains, the bright green, and black spinels. Occasionally, some of the nodules yield larger gem-quality grains. Many are fractured but can still yield gemstones of a few carats in size. More rarely, nodules consist of all large grains. The possibility of producing larger faceting material increases within such nodules. This is a view from near the summit of Peridot Hill, showing State Route 70 in the background, and the unpaved road that leads past the vent to the Peridot claims on the mesa. This field trip is being led by Stevie Joey. Stevie Joey is a native Arizonan. He was born in Phoenix and is half Apache and half Navajo. His aunt Willa Jean Brown had a claim on Peridot Mesa that Stevie inherited. For the past 11 years, he has been working the claim on and off. In September of 2012, he rented a backhoe and exposed a new area in his claim. Stevie says, this is a quote, "I feel comfortable and free up there thinking about the next peridot pocket I will hit. It is very addictive. After you hit a good pocket, you have peridot dreams. My dreams get bigger and bigger along with my peridot ambitions. I can't wait to go back again." This is a view that shows a producing wall inside Stevie's claim. On this field trip, we were allowed to collect along the walls and tailings. Here, Stevie is using a gas-operated generator to power a jackhammer. The work is slow and hard, but he is persistent, and his work is often rewarded with quality stones. Scanning carefully through the freshly broken material, Stevie is able to select stones that are of the best quality. At the bottom of this slide is a link to a YouTube video of Stevie collecting on the day of this field trip. After collecting suitable candidates for faceting, Stevie places them on a screen to select the larger ones for further investigations. Most of the lherzolite xenoliths are not worth the effort of breaking apart to look for a larger gem rough. Although there most likely are some worthy stones in the mix, it is not productive enough to break apart each nodule. But Stevie's guests at the claim are welcome to investigate and collect from these piles. Each of these rocks in itself is a geological treasure, representing the extreme conditions found many miles below our feet. In some cases, the next step in determining the quality of the peridot is to tumble them. This process not only cleans and polishes the surfaces, but in many cases breaks the stones along existing or hidden fractures. Once they are polished, it is much easier to determine the potential value as a faceted stone. From the rough stones, a few are selected based on their color, clarity, and lack of flaws. These are used to produce the finished faceted gemstones. Notice, trespassing on the San Carlos Indian Reservation can result in imprisonment and a fine. Obtaining a permit does not allow you to collect Peridot on Peridot Mesa. You must be accompanied by a claim owner. Collecting any rock on the mesa without permission of the claim owner is a very serious offense. So just because the information provided in this PowerPoint indicates what is on the mesa and how to get there, it is illegal to be on the mesa without proper papers and a guide.